Here's Keanu Reeves with his classic look. Alright, I will do my best to explain this type of problem better. Alright, we have a stationary box of mass M is pulled across a frictionless horizontal floor by a constant force F that is at an angle theta above the horizontal. And it says here, assume the box does not lose contact with the floor, meaning it does not fly up. Okay, so here's the diagram. We have a box of mass M. The force being applied is a diagonal in the northeast direction. We don't know what F is for now. And then the angle is given us as theta and the surface is frictionless. So not too bad. All right, so here's part A, B, C, D, and E. If you like to, pause the video and then read it for yourself and maybe before you keep up. All right, I'm just gonna go ahead and tack it to save some time. Part A, B, C will be done on this particular slide. Part A asks us to derive an expression for the acceleration in terms of the variables given in any fundamental constants as appropriate. So here, because the problem initial states that it does not lose contact with the floor, so I would assume that it is accelerating to the right because the force is being applied right and up. And because it does not lose contact, it would imply that the force, or the mass, excuse me here, is being accelerated to the right. All right. In order to find the acceleration function, we need to set up the information using Newton's second law in the horizontal direction. So here you notice I did sigma FMA, but for F I put subscript X. For A I also put a subscript X because it's going to accelerate to the right in this particular problem, since that initial condition given is in the initial condition is given to us. It says assume the box does not lose contact with the floor. All right, so therefore to do this I need to figure out what all of my horizontal forces are. So in this case it's pretty straightforward. There's only one, because the only force that's presented to us here is this force that is diagonally directed northeast. So therefore I know my horizontal component is f of x, which is pointing to the right, or aka east. All right, to figure that out, all we have to do is you do a little geometry. Cosine of theta by definition is adjacent over hypotenuse. Our adjacent in this case is f of x over our hypotenuse, which is f. So therefore cosine of theta is equal to f of x over f. Now we need the isolate for f of x because that's what we need down here. The only force in the horizontal direction for this particular problem is f of x. So therefore to get f of x by itself, we need to multiply both sides by f to get rid of this denominator. But what we do on one side, we do on both sides. Therefore, f of x is equal to f times cosine theta. So now that we know what f of x is, which is f cosine theta, we can go ahead and do this quick substitution because the problem asks us to find the acceleration in terms of the variables given. F of x is not given, but f is and theta is. So we can replace f of x with f cosine theta, which is equal to mass times acceleration. And therefore, to isolate for ax, we divide both sides by m. Therefore, the final outcome is going to be f cosine theta divided by mass. And this is our expression for ax for this particular problem. Every problem is going to be a little different, okay? All right, let's do part B. Part B asks us to derive an expression for the normal force exerted by the floor onto the box in terms of the variable given, okay? So in that case, because it asks for f of n, I know I need to focus my attention in the vertical direction because f of n is perpendicular to the surface, and the surface being horizontal for this problem, therefore perpendicular to the surface would imply the y direction. So I need to draw all my vectors out in the vertical direction. All right, so the first arrow that just came up here on the screen, that is my normal force, the force exerted by the floor onto the box, and then the weight of the box itself. Anytime you have a mass, there is a weight. In this case, weight I have just labeled as force of gravity, which is the same thing, times mass, which equals mass times acceleration. And then I need to also write out the vertical component of the applied force, because this force here is a diagonal. It is pointing right and up. I know that I have a component Fy, which is directed upward. Therefore, it's not too bad to do. I need to figure out what f of y is by using the same strategy that I did with f of x. F of y here is my opposite relative to this particular angle reference. So therefore, sine of theta is equal to opposite over hypotenuse. So if I reference this angle, opposite would be f of y over my hypotenuse, which is f. Now to find f of y, multiply both sides by f, which is the same scale set. Therefore, fy is f sine theta. So therefore, we can go ahead and simplify the sigma notation here. This is to add up all the forces in the vertical direction. Okay, and therefore the one thing that we need to focus on here is just labeling and including all the vertical components and the force themselves. Here I have f of n pointing up, which I included there. I'm going to add it with the stuff that points in the same direction. In this case, upward. F of y also points upward. And then, so you're noticing in this diagram, I have f of n pointing upward, I have f of y pointing upward, so I'm going to add those two together because they're pointing in the same direction. However, f of g, which is a vector that's keeping the mass in the box, or excuse me, the box itself on the floor, so therefore f of g is pointing downward, and therefore I subtract it. But I do want to point out here though, subtracting it already includes a negative sign in g. Okay, and this is usually where folks get confused. By definition, g is negative 9.8. However, I already introduced a negative sign here, so therefore, when you plug in values, you should only plug in 9.8 because I've already accounted for the negative sign. So the way I do physics here, I already accounted for the sign. Okay, here mass just gets carried down. Ay here, you notice though, is substituted with the 0 because the original statement says assume the box does not lose contact with the floor. All right, so that's an important statement. Because it does not lose contact with the floor, it implies that ay is 0 because the object is not accelerating up or down. It is only accelerating in the horizontal direction for this particular diagram. All right. In that case, to solve for f of n, I need to get rid of this fy and this f of g. So therefore, moving f of g or negative f of g to the right side of the function changes the sign. So it goes from negative f of g to positive f of g. And then this positive fy component, now if I move to the other side of the equal sign, it would now be negative fy. So therefore, I can go ahead and substitute the two variables here, or the two functions here. F of g is equal to mass times gravity subtracted from f of y. But if you have been keeping up along, f of y here is f sine theta. So I did this quick substitution so that it's in terms of the variables given to me, which is f and theta. Okay, m is given in and g is one of your universal constant or your fundamental constant. All right, so this would be our expression for f of n. And I made a note for folks here if you do need to keep this in mind. Again, if I was doing this mathematically, at this point I would plug in a positive 9.8 because, as I said earlier, the negative sign is already accounted for in my work. So when you do physics, you have to make these choices and be consistent with them. I like to introduce my negative sign right away so I don't forget about it. All right, so that's that. So that is our function for f of n in terms of the variables given, which is m, g is the constant, and then f is given and theta is given. So that would be our expression. All right, that's the answer to part B. Part C asks you to find the acceleration, or excuse me, how does the acceleration of the box change if theta is increased? So in this diagram, theta is vague here, it just gives us theta. So therefore, all we have to do is look at this function here on the left side. So keep up here, yeah? Acceleration is f cosine theta over m. Well, all you have to do is conceptually think about it or use your calculator if you need to. Here, I've used in a few different values just to help you conceptualize stuff. Here, I just picked some random angle. I picked cosine of 10. I punch out my calculator. The answer is 0.9848. And then I went to cosine of 40, which is 0.766. So as you can see here, as the angle gets bigger, yeah, the value of cosine goes down. It decreases. Okay, so here I have cosine of 70, which is 0.34. So when the angle is small, cosine is big. Well, that makes sense to me. When the angle is small, majority of your vector is focused in the horizontal direction, which implies that it would be big. So as you increase the angle, sine increases and cosine decreases. So in this case, as the angle increases, cosine decreases. Okay, so my final answer for this one that I would say, because it asks for how does the acceleration of the box change if theta is increased. Well, if theta is increased, cosine decreases. So in this particular function here, we have f cosine theta. As the angle gets bigger, cosine gets smaller. As cosine gets smaller, the product in the numerator gets smaller because you're multiplying by a smaller number. And you're dividing by the same constant on the bottom, which would suggest that the answer is getting smaller and smaller. Okay, so conceptually that makes sense to me. It says ax here decreases as theta increases. So as the angle gets steeper and steeper, your force is less and less in the x direction. Because it is less and less in the x direction, the acceleration becomes less and less as well. All right, so that is the answer for part C. For part D, it says here, how is the contact force affected when the angle theta is increased? So as theta increases, f of y increases, but as f of y increases, f of n must decrease conceptually. All right, so I just carry my work here from the previous slide. It says here sigma fy equals may, and then I include all my components. I did fn, which is pointing up, plus fy, which is also pointing up. Subtract it from the vector that's pointing down, which is the weight, or aka the f of g, which is equal to mass times 0. Okay, so again, if you kept up with the work in the previous slide, f of n is now equal to f of g minus f of y. Therefore, expanding f of g, we have mg, but again, here g, I would plug in a positive 9.8 meters per second square, and then f of y is just f sine theta, which is on this side. So I kept all the work over here. All right, now it asks us to assess how is f of n affected, right, when theta is increased. So based on this particular function here, f of n is mg, m is a constant, g is a constant, and we're going to subtract it from f sine theta. Well, here again, I've chosen just some random angles just for you to help visualize. So if your math skill is good, I think this is easy to do, but if not, listen here. Sine of 20 is 0.3420. And then I increase the angle to some random angle 50. Well, as you can see already, as the angle gets deeper from 20 degrees to 50, sine of 50 is 0.7660. So the answer just got bigger. Now, I want to take it one more step further. I want to do sine of 80 degrees. Well, sine of 80 degrees is 0.9848. So as you can see, increasing the angle from 20 to 50 to 80 causes sine of theta to increase as well. Well, conceptually speaking, well, f times sine theta. But if theta here increases, this whole sine theta increases. So therefore, f sine of theta will also increase. So I drew a few arrows here for you. As theta increases, this component increases, and it keeps increasing, and it keeps increasing, which implies that you're subtracting by a bigger number every time. So m and g are constant, but if you keep subtracting by a bigger number, by a bigger number, by a bigger number, your outcome is going to get smaller and smaller, which makes sense to me, okay? So here I have the statement. It says f of n decreases as theta increases. So in this particular diagram here, hopefully this is hopefully this is making sense to you. I have one vector pointing down, which is constant. The weight of the object cannot change in a given problem. So it's just mass times gravity. So therefore, watch my cursor. If sine increases, this f of y has to increase. But if f of y increases, this f of n vector has to decrease, because fn plus f of y equals f of g. So therefore, when f of y increases, f of n must decrease in order to give us the same answer pointing downward, okay? If you need to, listen to that again. All right, let's do part E. It says here, if the mass is 15 kilograms and the applied force is 30 and the angle is 27, calculate the box's velocity at 2.7 seconds. Not too bad. Well, in order to find the velocity, we need to find the acceleration. And as I stated earlier, the only acceleration that exists for this problem is in the horizontal direction, okay? Therefore, we can just expand sigma fx. For this particular diagram, it's only one component, which is f of x, which is equal to max. But f of x is equal to f cosine theta, which again is pulled from here where I'm circling with my cursor. F of x is simply f cosine theta. We know what f is. F is given to us, so let's go ahead and plug this stuff in. F is equal to 30, cosine is equal to, cosine of theta, and theta is equal to 27 degrees, and then mass is 15 kilograms. So if we simplify this on a calculator, the numerator becomes 26.73 newtons divided by 15 kilograms. Therefore, our acceleration in the horizontal direction is 1.78 meters per second squared. All right. To find the velocity at 2.7 seconds, though, we can use our kinematics. Our final velocity at any given time is simply acceleration times time plus vi under constant acceleration, which it is in this case because the force is constant. Therefore, A is placed with 1.78. Our time here is 2.7 seconds. VI is 0 because it says a stationary box. Stationary imply that the initial velocity is 0, so therefore I'm going to leave that term out in my work. If you do 1.78 times 2.7, you get plus 4.8 meters per second. Here I've chosen to include the the plus sign, because it asks for velocity, which is a vector. Okay, man, it's hard recording these videos late at night. All right, so hopefully that helps. Good luck. Stay nerdy.